expected value. Expected value. So I'll say what it is. In our examples 2 and 3 are on this, and then we're done. So let's suppose x is a random variable with probability distribution let's say it's given by the table. Let's just do n different values of x, and then the probability that x will have that value. So I don't know the values of x. Let's call it n1, n2, all the way to nr. I don't know. X could have many different values. I can make a general statement here. And I have probabilities. Let's call them P1, P for probability, P2, all the way to PR. I have a probability that goes with every value. I don't know how many there are, so I have to have something a little bit more general. The expected value of x is defined as e and x in square brackets, because I need to know which random variable I'm talking about. E for expected value, and then x, square brackets for some reason, is the standard. It's just a combination of these guys. How do I combine them? I take the value of x, the first value, times the corresponding probability. Take the second value times its probability, and add them all up until I get the last one times its probability. And I'll get a value. Now, I'm not really motivating these because I've done it in the past and it creates more confusion than I want. So through the examples, we'll get a feeling for what this is trying to say. But this is sort of, we're weighting the different values of x according to the probability. So if one of these values has a very high probability, then it'll sort of have more influence on the expected value in the end. If this n1 has a very small probability of happening, then because I'm multiplying them, this guy is going to be really small. And its contribution to this expected value is not going to be much. So this is a way to measure what the likely outcome is. If, let's say here, expected value of x is a way to measure or to say or to indicate is the word I'm looking for. Indicate what the likely outcome, let's say here, might be. A little vague, because if you were to do this experiment, you can get any one of these values. Some are more likely than others, but you can get any of them. If I play the lottery, if that's something you do, regardless of how unlikely it is to win, it can still happen. But if I were to do something like that, what do I expect to happen? Do I expect to win? No, there's no way I can expect to win. So we'll look at more specific things, but the expected value will indicate what is likely to happen. And the outcomes with the bigger probabilities will be more likely to happen. So I think let's just look at some examples, and then it will be much better. So this is the formula that you have to remember. Now let's just see how to use it, and what does it mean when I do get an expected value? All right. So I enjoyed these two examples because they're nice and practical, and that's the whole point of this lecture. So let's read it. For a weekly raffle, 1,000 tickets are sold at $2 each. There is one first prize of 100, 2 second prizes of 50 each, 7 third prizes of $20 each. Determine your expected winning by 1 ticket randomly. So if I were to play this, what do I expect is going to happen? Another way of saying it is, let's suppose this happens every week. Then if I played this every week, in the long run, do I expect to make a profit? Do I expect to lose money? It depends on the numbers. It depends on how likely it is to win a prize, and so on. So so this gives me a way to examine this situation more accurately. So we need to find a random variable. I'll just call it x. Let x represent the, let's say, my net winnings. If I played this once, what are the possible values of x? That's my next step. What are the possible values of x? Let's do them in increasing order. So what is the, well, it doesn't really matter. Whatever comes first. Let's maybe do it decreasing. If I were to win first prize, what is the corresponding value of x that represents that outcome? Not probability, the value. Not doing probability. The value of x represents an outcome. If I'm interested in the outcome that I win first prize, what is the corresponding value of x that represents that result? 100. I win 100, but it costs me $2 to play. So I've won $98. Does that make sense? So talking about a variable x and an associated value, it's just a different way of representing an outcome. A different way. So when I say x equals 98, that is the same as saying I win first prize. It's a different way of saying the same thing. So we have to get used to, when I look at this, I see this. But I can't do this in any formula or any calculation. It makes no sense. So I write this, I represent that outcome in a different way so I can work with this and make conclusions about the experiment. What else can I get? What's the next best value I can get?
48.
48? What does that correspond? If I win second prize, I get 50, but it costs me $2, so I win 48. And the next one? 18, if I win the next prize. Is that it? I have to make sure I cover all the possibilities. For anything that can happen, there should be a value of x represented.
Minus 2.
Minus 2. That represents where I win nothing. I lost $2. So I won negative $2. I can't exclude this because then I don't have all the possibilities. I need to cover all the possible cases. Now let's make a little table. It doesn't really matter how we do that. Let's say this is now the probability distribution of x. Let's make a little sideways table this time. So I'll have the value of x and the probability that x has that value. So I'll have 98, 48, 18, and negative 2. What is the probability that x has the value 98. That's just another way of saying what is the probability of winning first prize. 1 out of 1,000. Everyone happy with 1 out of 1,000? There's one ticket that'll give me first prize, but there are 1,000 possible tickets. So it's the same type of probability calculation. Number of ways I can get what I want, divided by all possible ways. What about the second prize, which is represented by x equals 48?
1 over 500.
Well, I don't want to simplify it. Otherwise, I forget where it comes from. I want to leave it as clear as possible. How many ways can I get second prize? And there are 1,000 possible tickets. You're right, 1 over 500 is correct, but there's no need to simplify it. I want to see where it comes from. Let me put these guys at the top there. I want to write nice and big. So let me just do my headings again. Next one is 18. How many third prizes do I have? 7. And then -2. How many ways can I get nothing if I play this? 10. A lot of numbers floating around. But let's assume that's what he said. The remaining ways, I'm going to win nothing. So the check is, does it add up to 1? If it doesn't add up to 1, then either one of these probabilities is not correct, or I didn't cover all the possibilities. So I have a check put in. They should add up to 1. And if they don't, then maybe I just wrote something wrong, or maybe I'm actually missing a possibility that I need to add. Does it add up to 1? I'm pretty sure it does. So that doesn't guarantee that I'm right, but at least it tells me I didn't make a serious mistake. I can at least exclude the common mistakes. Any questions on this so far? So now I have my random variable, the possible values, I have the corresponding probabilities, and all I need to do is plug that into my expected value formula, if you will, and get a value. So the expected value, I'll write it out, and then you can calculate it for me. I'm never calculating it. What did we say? It's the first value times the corresponding probability plus the next value times the corresponding probability plus the next value times the corresponding probability plus the next value times the corresponding probability. Is that right?
The -2?
Yeah, it's the value. And the value is -2. So be careful of that. You can plug this in and tell me what you get. So this is all multiplied. These guys are multiplied, these guys are multiplied, and so on. Remember the negative, otherwise it won't work.
So this is something we will have to do?
Yes. This is the likely type of question in an exam. It's really only one type of question. And I like the raffle setting because it gives me some probabilities, but they're not complicated to get. Does anyone have a number? Doesn't matter if it's wrong, we're not testing calculator skill. But in a question like this, I do want this number to be correct, otherwise my interpretation might not be right. What do you get? Everyone's just sitting back and letting someone else worry about it. In the test, you have to do it.
I think I got it wrong.
It doesn't matter.
It says negative 1.6.
Can anyone confirm her
But that
negative
too.
1.6?
It makes sense because you're more likely to lose $2 than to win.
Oh, okay.
Don't be careful. Don't be careful. Don't assume that this should be negative. So if you get a negative number, it's right. It's I can easily set this up with different probabilities that you're talking about. The numbers combine in such a way that it gives me this number. I can't assume, well, of course it's going to be negative, and then put a negative number there. Be careful. How do I interpret this negative? What does that mean? So the expected value tells me something about what I can expect, hence its name, if I were to play this game or take part in this raffle or something. It tells me something about the long-term effects or the long-term outcomes, I guess. If I were to do this experiment over and over and over, and I take an average of all those winnings, yes, I could play this next week and I could win $1,000. Then I'm up 1,000. But if I keep playing, am I going to stay in the positive? This is what that number tells me. It says if I play long enough, I'm going to average around $1.60 in the negative per game. So let's say here in the long run, we can expect to lose. That's right over here. This tells me what I can expect will happen if I did this long enough. So I can expect to lose roughly $1.66 on average per game. Per game, let's say, whatever the experiment is. So that says a lot of things. That says if I were to do this and I win a prize, maybe stop. Because if I play long enough, I'm going to lose all that money. Yes? Standard deviation is the next one. Standard deviation tells me how the outcomes are spread around this. Meaning, if they're packed very closely, I'll have a small standard deviation, meaning that I'm going to often get a result close to this guy. If the standard deviation is very big, then I can get very extreme values more often. It's a little different. Yeah. But in statistics, this one was standard deviation. They each tell me something, but it's different. And then you get a bunch of others after that, each one telling me something. This is the one we start with, so it's the only one I'm going to worry about. It at least gives me an idea. I don't know. If I play next week, I could win 1,000. I could win nothing. But because this probability is so much higher than the others, in this calculation, this sort of weighs down the -2 to have a much bigger influence on this final number. That makes sense. So it's important that we can interpret this. Let's do one more, which is very similar, so just to make sure. And this is the typical kind of question. So there are these two. There are two in the homework that you can do. They follow very similarly. And I think among those four, it should prepare you fairly well. Let's consider the following game. Two balanced 6-sided dice are rolled. If double sixes are rolled, the player wins $10. If doubles of any other number is rolled, the player wins $5. But if the two numbers on the dice are different, the player doesn't win anything. On a single play, what is the expected amount that the game operator will have to pay out to the player? So this one's a little different in what my variable represents. Let's pretend there's a little games table at some benefit or something, and I'm trying to decide, should I play this? I'm trying to make money for charity or something. So if I'm running this game, I want people to lose so that they're actually donating without realizing it. So I want to make sure my numbers work in such a way, and the amount that they can win, that those numbers are such that they do lose in the long run, which means we're making money in the long run. I want to make sure it's designed well. So let X represent, I have to look at the question, let's say the payout. The amount that I will have to pay. Then possible values of X is my next step. Notice how our steps are the same between these two values.
But here you mean amount that you have to pay?
So pretend now I'm the person running the game and someone else is playing.
Okay.
What are the different values, what are the different amounts that I would have to pay? Values. What are the different values? Now the worst one is if they win $10. So it's not costing them anything at this point. Now what is the next best? Or the next worst for me? If they win 5. Are those the only outcomes or the only values of X? 0 is necessary because it represents the case where they don't win anything. So I only have 3 of them here, which is nice. And I need to find the probability associated with each value of X. So the steps here are not very complicated. I should have to do them one at a time. So let's say here probability distribution. How are the probabilities distributed over these values? It doesn't matter how we do it. Let's do a sideways table, I guess. I have my values and I have the probability that X has one of these values. And my possible values are 10, 5, and 0. So what is the probability that X equals 10? Just another way of saying what is the probability that the player wins $10? So how can the player win $10? Well, I roll 2 dice, and I want only one possible pair, double sixes. So there's only one way to get it out of how many?
36.
36 possible pairs, 6 times 6. Only one. 5 means, X equal to 5 means that they win the second prize, the other prize, which is when they get any other double. What is the probability that that will happen? 5 other doubles over 36 possible outcomes without any restriction. So then the rest has to be everything else. So it has to be 30 over 36. So you don't even have to calculate this. They have to add up to 1. This has to be everything else. But by doing that, I lose my check, because now I've sort of used the check, the knowledge that they have to add up to 1 to fill that out without really much effort. There are 30 other possible pairs of numbers that are not doubles out of 36. So now the expected value, let's write it out. The value 10 times 1 over 36. The value 5 times 5 over 36. Plus the value 0 times 30 over 36. I'll write this even though it gives me a 0. To show that I've calculated it completely. Rather show too much than not enough. What do I get? Sorry, so I want a decimal number. Just to make it simple. Decimal number?
0.97.
197?
0.97.
0.97? Can anyone confirm his 0.97?
Yes.
Okay. So this tells me the interpretation is important here as well. So what does this tell me? What does it tell me? What do you think? It has to tell me something. That's the whole point of doing this.
We leave it in just the functional form of the test.
Oh, no, it's fine. I just can't wait to see exactly how big the fraction is. The decimal numbers makes it easier. It doesn't matter how you present it. What does that 0.97 tell me? If I'm now pretending I'm considering playing or hosting this game, I want to win money for whatever reason. So I want players to lose. And as it stands now, on average, they're going to win 97 cents. So what does that tell me? If I want to design a game.
You want to make whatever they're paying in order to play be higher than 97 cents, so you make a profit.
So this tells me that in the long run, if I leave it like it is now, on average they're going to win 97 cents per game. So we can say charge just anything more than 97 cents. And the host will make a profit. Now there's a balance. I mean, when you're actually trying to implement this, if you charge too much, then fewer people will play, and this expected value is a long-term estimate. That if people play forever, or the longer people play, the closer it'll get to this value. Meaning that if I charge too much and only a few people play, then what I can get as a result will differ greatly from this. The more people that play, the longer the game goes, the closer it'll be to this average. So it's sort of an ideal number in a way, telling me if you play this game forever, or a lot of people play it, on average this is going to happen. If I don't do it often, if I don't do a lot of repetitions, or not many people play, then what I can actually get could be very different from this. But it gives me a way to look at the experiment and see what is this a good idea? Is it not? What can I do to make it better? And things like that. So the interpretation of the expected value is an important step as well. So take note of the steps. We always do the same steps. Either they define x for me or I do it. All the possible values of x, then the probabilities, calculate the expected value, and make a conclusion and interpret the result. Any questions on this? Yes?
How many decimals per place in this distribution?
Oh, I really don't care. 2 decimals, fine. 2 decimal places. We're not uptight about those things.